You may have noticed that in vector calculus, things come in threes. There were three kinds of derivative, three kinds of integrals, and now I'm going to tell you three theorems that relate derivatives to integrals. These are all special cases of a general result known as Stokes' theorem, and they can be thought of as generalizations of the fundamental theorem of calculus. Remember, the fundamental theorem of calculus says that if you integrate a derivative, you just get the value of the function. Well, the fundamental theorem for gradients says that if you line integrate the gradient of a function, you just get the value of the function at the two ends. Now, the fundamental theorem for curls is a little different. It says that if you surface integrate the curl of a vector, you get, well, something involving the vector at sort of the edges, but not just the value at one point, because the edge is a whole curve. You actually get a line integral of the vector field over the curve. And the last incarnation of this theorem is called the divergence theorem. It tells you that the volume integral of the divergence of a vector is given by a surface integral of the vector, where the surface is the surface bounding the volume you considered. So all of these theorems relate the integral of a derivative on one domain to a lower dimensional integral of the function itself. In this video, I'll go through each of the three theorems, discuss what it means mathematically, and what role it plays in physics. Let's start with the fundamental theorem for gradients. This theorem says that if you line integrate a vector field that is actually the gradient of some scalar field f, then the answer is just given by f evaluated at the end point minus f evaluated at the start point. This one is very similar to the ordinary fundamental theorem of calculus. In fact, you can prove it starting with the parametrized definition of the line integral that I gave in the previous video. Now, you can use this theorem if you are given the gradient of a scalar to integrate, but usually you're given some vector field, and you want to know, is it the gradient of a scalar? Well, we answered that question already in the previous video on derivatives. Remember, there's a theorem that says that if your vector field has zero curl over the region of interest, then your vector field can be written as the gradient of a scalar. A vector field with zero curl has a special name. It's called conservative. A conservative vector field has some very special properties. We see directly from the theorem that a conservative vector field's line integral doesn't depend on the path you take. It only depends on the two endpoints. That's a very special property of conservative vector fields. Also, if we consider a loop for our path, now the two endpoints are the same, and the theorem tells us that the line integral vanishes. So the line integral of a conservative vector field around a closed loop is 0. These properties are very useful conceptually and, for example, underlie the conservation of energy. But they're also useful in practice. When you're asked to compute a line integral of some vector field, first check if it's conservative. If that vector field has zero curl, there are some tricks you can use. Of course, you could just try to find a function f, whose gradient is that vector field. One exists, but it may be hard to find. If you find it, you've computed the line integral you want. In fact, you've computed any line integral you could possibly conceive of because they're all just given by f at one point minus f at the other point. However, even if you can't find the f, there are still some tricks you can play. Suppose you needed to compute the line integral of a vector field over some very complicated path with 17 curlicues through space. Well, if your vector field is conservative, you just pick a different path. Pick a straight line between those 2 points. It doesn't matter. The answer is independent of the path. So this can be very helpful computationally. Even if you can't find the f, you can just change the path and you know the answer will be the same. Now let's talk physics. The fundamental theorem for gradients is actually a theorem you've already met. It was called the work-energy theorem. You've probably met this in one dimension. It just says that the work done by a force is equal to the change in energy of the particle. Well, this theorem is the three-dimensional version. The integral of a force, F dot dr, over some path in three-dimensional space is just given by the difference in the potential, phi, if F equals the gradient of phi. And I'll warn you that usually there's a conventional minus sign. We write F equals minus phi when we introduce potentials for forces in the work energy theorem, but it's the same theorem. Now we come to the fundamental theorem involving curls. This theorem says that if you do the surface integral of a vector field that happens to be the curl of another vector field, then the answer is given by a line integral of that other vector field over the bounding line to the surface. Now here we have to worry about orientation. Here's how you figure out which way you're supposed to go around the bounding line or curve. You take your right hand and you put your thumb through the surface in the direction you've chosen as the orientation for that surface integral, i.e. the direction that the normal vector is pointing in integral of v dot dA. Then your fingers on your right hand curl around in the direction you're supposed to take for the line integral along the boundary. That is, it's the right hand rule. Now, if you're given a vector field that is the curl of another vector field, you can just use the theorem. But usually you find yourself in a situation where you're doing the surface integral of some vector field w, and you're wondering, is that vector field the curl of some other vector field v? Well, there's a condition that we talked about in the video on derivatives. Your vector field can be written as the curl of another vector field if and only if it is divergence-free over the region of interest. So, if you're doing a surface integral, check if your vector field has zero divergence. If it does, we call it a solenoidal vector field, and this theorem is going to be useful to you. Solenoidal vector fields have some very special properties. The integral over some surface of a solenoidal vector field depends only on the boundary of that surface. It doesn't matter what the surface is doing away from that boundary. It could wiggle around in different ways. The answer will depend only on the loop that bounds the surface. And second of all, if the surface is closed such that that bounding loop shrinks to zero, then the surface integral is zero. You can also use this theorem to compute by either finding the vector field whose curl is your vector field or changing the surface to a different one, but it doesn't come up so commonly. Now, solenoidal vector fields are all over physics. One really important example is the magnetic field. The divergence of the magnetic field is zero. That's a law of nature. This means that the magnetic flux through a surface depends only on the loop bounding that surface. And so you can actually just talk about the flux through a loop. That's a well-defined quantity. And that underlies a lot of intuition in magnetized plasma physics, for example. Another example of a solenoidal vector field is the velocity field of an incompressible flow, and the mathematics of this theorem plays a key role in the fluid dynamics of incompressible fluids. Finally, let's talk about the fundamental theorem for divergences, which is more commonly known as the divergence theorem. This theorem says that the integral of the divergence of a vector field over some volume is given by the surface integral of that vector field over the surface bounding the volume. For the orientation of the surface integral, you are supposed to choose the outward normal. The divergence theorem comes up a lot in physics, and you'll meet it again and again. It's fun to just check it with some simple examples. So if you remember from the integral video, we computed the flux through a cube of a particular vector field. It was a bit painstaking, and I only did 2 of them in front of you, but after we added up the flux from all 6 faces, we got the number 2. Well, let's check the divergence theorem by taking the divergence of this vector field and integrating it over the interior of the cube. Now we have a relatively simple triple integral to do, and after some calculation, you again get 2. So the theorem works as it must. The last thing I want to tell you about as part of the video on the fundamental theorems of calculus is the technique known as integration by parts. You've probably met this in terms of one-dimensional integrals as a trick for doing them. In terms of volume, surface, and line integrals, it becomes a much more powerful technique that comes up again and again. Let's think about the one-dimensional version. We derive it by starting with the product rule for ordinary derivatives. The x derivative of f times g is df dxg plus f dg dx. Now, if we integrate both sides after some manipulations, we get the formula you're familiar with, which lets you sort of switch which term the derivative is on at the cost of this f times g term. This f times g is evaluated at the edges, a and b, of your integration domain, and it's the kind of boundary term. So when we do similar things for the vector calculus fundamental theorems, we're again going to be able to move a derivative from one term to the other at the cost of a boundary term, except now the boundary might be a surface integral or a line integral. There are many different product rules for the various derivatives of vector calculus, and you can look them up in tables, on the internet, in books, wherever you like. I'll do an example here of using one common product rule to perform an integration by parts manipulation. This product rule says that if you take the divergence of a scalar f times a vector v, what you get is the divergence of the vector v times the scalar f plus the gradient of f dotted into v. It couldn't really be anything else by the notation, and you can remember it that way, but I would always recommend deriving it or looking it up to make sure. Now let's integrate both sides of this equation over some volume of space, i.e. do a volume integral d tau. On the left-hand side, we have the integral of a divergence, the divergence of f times v. So we can use the divergence theorem to replace that with the surface integral of f times v dot dA. Now we can rearrange the terms into a nice integration by parts formula, which tells you that if you're ever doing the volume integral of some scalar times the divergence of a vector, you can swap that to the gradient of the scalar dotted into the vector at the cost of a minus sign and a boundary term. Many such other integration by parts formulas can be derived. I'll conclude the video by mentioning that while there's undoubtedly a nice symmetry to all of this, 3 derivatives, 3 integrals, 3 theorems relating them, it is a bit of a mess, and it can be hard to see how it all fits together. I certainly felt that way when I first encountered it. And to be honest, I was never completely satisfied until I started looking at it from a totally different perspective. This is the perspective of differential forms, where there's a general theorem called Stokes' theorem, which nicely encapsulates all of these 3 different results. I can't get into all of that in this class, but I definitely recommend that you read about it because it's a truly beautiful piece of mathematics that is ubiquitous in physics.